In this video, I'm going to talk about sampling distributions and also the central limit theorem. So sampling distributions are a representation of all possible values of a statistic. It can be a representation of all possible values of a sample mean, of a sample standard deviation, or it can be a representation of all possible values of a test statistic, such as z or t or f or chi-square. Some of these we haven't encountered yet and we'll encounter later in the course, but we have already encountered the standard normal distribution, which, as you recall, is symbolized by z and has a mean of 0 and a standard deviation of 1. So you can think of this as being like all possible values of z, where the most common, the mean, median, mode value is 0, and as we move farther out to the right or farther out to the left, the probability of, let's say, selecting one of those values by chance or encountering one of those values by chance becomes much lower, whereas when we're near the center of the distribution, it's much higher. So there's different sorts of sampling distributions, and just this isn't very practical, but say you wanted to create a sampling distribution, you would want to determine all possible samples of size n, right? So that in itself is not very practical. And then calculate the statistic repeatedly for all possible samples, basically infinitely. So this isn't a practical way to do it, but it's a way to think about it. And then we could calculate the probability of each value occurring, or we could calculate what's called the density function for each value, which would basically be equivalent to the height of the value on the y-axis. So that's one way to think about creating a sampling distribution. Of course, sampling distributions are defined by formulas, so there's really no need to go through this process, but it's one way to think about how a sampling distribution could, in theory, come about. So one sampling distribution that will be important to us, besides the z distribution, which we've already encountered, is a sampling distribution of the mean. So think of it in terms of, okay, sample mean, not population mean, in terms of sample mean. So let's say we're taking an infinite number of samples of size n. So let's just throw out a number. Let's say the n, the sample size, is 20. Each sample of size 20 is going to yield its own mean. Now, those means aren't always going to be the same, so there will be different sample means. However, if the samples are at random, the mean of all those possible sample means, it's getting a little complicated, but we're taking a lot of sample means from a population, and we're calculating the mean of those sample means. That will actually equal the population mean. Now, any given mean, let's say we're sampling from a population with a sample size of 20, any given mean may be different from its population mean, and we could call that difference between the sample mean and the population mean, we could call that sampling error, which is defined by a statistic called the standard error of the mean. The standard error of the mean is basically how different, let's say on average, we would expect our sample mean to be discrepant from the population mean it should represent, assuming the samples are sufficiently large and taken at random. This brings us to an important concept in statistics called the central limit theorem. So regardless of the shape of the parent distribution, so the distribution in the population, we'll call that the parent distribution, the sampling distribution of the means, which is basically the distribution of the sample mean. So if we repeatedly sampled those means, it will be normally distributed basically regardless of the shape of the parent distribution, provided that the samples themselves are sufficiently large and taken at random. And what is sufficiently large? This seems to hold and work out if samples are even as small as 5 or 10, as long as they're taken at random. Also, the mean of the sample mean, so if we repeatedly sample at random from a parent population, the mean of the sample means will equal the population mean. And the standard error of the mean, as we've already mentioned, can be defined as the population standard deviation divided by the square root of n. So mathematically, we can define these basically what we're going to think of as the standard deviation of those sample means. It has a specific term called the standard error of the mean, which is the population standard deviation divided by n. Alternatively, we could define it, they're mathematically equivalent, as the square root of the population variance over n. So you just take the population variance over n and then take the square root of that. So I want to demonstrate using this simulator, which hopefully will work on this computer. I've got to do some adjusting. Give me a moment. There we go. Okay, so this is really beautiful. So get some tissues or something, because you may actually experience tears of joy. So here we have the parent distribution. There are some limitations to the graphics of this simulation, but pretend that's a smooth normal distribution. And if we were to take samples of the mean, so we're taking mean, let's go with size 10, sample size 10, and let's take a sample of 10 from the parent distribution and plop down the mean. And you see it's not exactly right on, because the population mean is 16 and this sample mean was a bit lower. Let's go ahead and do it again and plop down the mean. And let's pretend we sat here all day and did this 10,000 times. What we will see is we've created a normal distribution. Given the limitations of the graphics here, we've created a normal distribution with a mean that's almost exactly the mean of the population. I mean, if we took another 10,000, maybe we'd get there. We've taken 20,000 samples of size 10. That's almost exactly the mean. That is now exactly the mean of the parent distribution. And notice the standard deviation of this sampling distribution in the mean is 1.59. Standard deviation up here is 5. So if we take 5 and divide it by the square root of n, which is 10, it'll probably be approximately 1.59, which basically is the standard error of the mean, or how much discrepancy we might expect a given sample to have away from the population parameter that it's supposed to represent. So it's kind of a beautiful thing to experience, but wait, hold on, there's more. Let's clear this out, and let's make a really just funky distribution. Let's make it look like a skyline of some city. And we've got a funky looking distribution here. It's certainly not a normal distribution. So what do you think will happen if we take 10,000 samples from this funky distribution? We get a normal distribution in the means. So what you've just experienced is the beauty of the central limit theorem. We get a mean of 14.89, which is really close to the population mean of 14.90, and we get a standard deviation of 2.07, which is approximately the population standard deviation divided by the square root of our sample size, which is 10. But more interestingly, we get a normal distribution of the means. So the central limit theorem states several things. The mean of the sample means will be the population mean, assuming the samples are at random and you took a sufficiently large number of samples and the sample size itself is sufficiently large. It also states that the standard deviation of the population divided by the square root of the sample size will give you the standard error of the mean, or the standard deviation of the sample means around the population mean. But more interestingly, it states that pretty much regardless of the shape of the parent population, If the samples are sufficiently large, and this seems to work with samples as small as 5, and taken at random, the shape of the distribution of the means will be normal. And that is a beautiful thing. So I hope you've enjoyed that demonstration of the beauty of the central limit theorem as much as I did. Thank you for listening.